Hello and thanks for tuning in. My name is Connor McAnuff and today I'll be presenting my project on predicting short-term solar energy production. This project was completed for the requirements of the Springboard Data Science Career Track Workshop. The project includes the classic aspects of a data science project culminating in building machine learning models for prediction purposes. All the Python code I use for this project is available on my GitHub. Check out the link in the description below. A quick overview of the presentation contents. We'll first be giving an overview of the task. Next, we clean and organize the data. Crucially, we perform exploratory data analysis to give insights into the data as a starting point. Next, we perform statistical data analysis as an exercise. We'll then go over the building, evaluation, and comparison of 3 types of machine learning models for this prediction task. Lastly, we'll reflect and make some conclusions on the project and its outcomes. First, a quick introduction into solar energy. At this point in time, I'm sure most people are familiar with at least the basics. Global capacity for solar energy generation has been increasing exponentially since 2006. The trend is expected to continue this way. One of the forms of solar energy generation is using photovoltaic panels to produce electricity through interaction with photons from the sun. Photovoltaic panels are likely the form of solar energy most people are familiar with. You can combine many of these PV panels to form a large utility-scale array for generating energy at the grid scale. How do you know how much energy is entering a PV system? You can use a pyranometer, which measures solar irradiance. Solar irradiance is often stated in watts per meter squared. Watts is a measure of power, 1 watt being equal to 1 joule per second, joules being a measure of energy. The solar irradiance in watts per meter squared can be summed daily to get a measure of joules per meter squared, which is the measure of energy available to enter a solar PV system on a daily basis. Now that we have a measure of energy available to enter a PV system, joules per meter squared, we can use this value to predict short-term solar energy production. The PV system configuration and associated energy losses through the system are well known. So, we can say that we are predicting solar energy production by predicting the solar energy availability for a given day at a specific location, the location being that of the PV array. How do we predict solar energy availability? It is in part determined by weather conditions. If we have weather forecasts for our PV array location, we may be able to use these forecasts to predict the daily solar energy availability. Why predict solar energy production at all? Why is this a useful task? Utilities companies distributing solar energy to the grid have a unique challenge. Unlike other methods of power generation, solar energy production can vary daily. A discrepancy between the expected energy production and the actual energy production can lead to an unbalanced grid, meaning energy shortages and surpluses. The shortages and surpluses are costly for utilities companies as they may result in making emergency energy purchases from another company or having wasted energy. Therefore, utility companies must be able to make informed grid balancing decisions to minimize costs and operations complications. The more accurately the energy produced from a solar PV array can be predicted, the more efficient the utility company's operations. The dataset was supplied for a Kaggle competition back in 2013. We are provided with a CSV file that holds a 98-row by 4-column array. The 98 rows are 98 Mesonet weather monitoring stations spread across Oklahoma. These Mesonet stations are to act as theoretical solar farm locations. We are provided with each station's ID, latitude, longitude, and elevation. The project objective is to predict the solar energy availability daily at each of these 98 stations, given weather forecasts. The second raw data file is also in CSV format. This array contains total daily solar energy availability, the target variable, at each of the 98 Mesonet stations from the beginning of 1994 to the end of 2007. The weather forecast data are provided in 15 separate net CDF4 files, one for each weather variable. The weather forecasts are sourced from a global ensemble forecast system. meaning there are multiple forecast models. In the case of these data, there are 11 predictive models and 5 forecast hours for each day. Additionally, predictions are made at 144 different locations, coinciding with the intersection between lines of latitude and longitude. To put that a little differently, for each day, at 144 locations in and around Oklahoma, each of the 15 weather variable forecasts are supplied 5 times daily by 11 different forecast models. These weather forecast variables will be organized and used as the machine learning features, that is to say, the predictors of solar energy availability. The full titles of the 15 weather forecast variables are displayed here. As you can see, they are different than your average consumer forecast of essentially temperature, precipitation, and humidity. Many of the variables are seemingly similar to each other and likely correlated. For example, maximum temperature over the past 3 hours at 2 meters above the ground and current temperature at 2 meters above the ground. Cleaning the data was fairly simple. There were no missing values. However, there were some fictional values input by the client when the parameters ceased functioning correctly. These values were found by their value counts and confirmed that they repeated for many days in a row. The fictional values consisted of less than 1% of the total energy data and have been removed. Formatting the data consists of creating a list of observations that include the date, station, solar energy availability, and the applicable weather forecast variables. Some decisions had to be made at this time regarding how to use the 144 forecast locations and how the 11 ensemble forecast models would be used. It was decided to keep it simple and use the forecast location closest to each station only. Additionally, only the median value of the ensemble forecasts are used. The 5 forecast hours are all kept and pivoted to be a column each. They will be tested as separate features. Okay, enough of the boring stuff. Let's visualize some data. Here, you are seeing a map of Oklahoma with lines of latitude and longitude overlaid. As said before, the intersection of these lines are the weather variable forecast locations. Each of the color points are Mesonet station locations, their color corresponding to the elevation of the station. The elevation increases from east to west, this trend being indicative of Oklahoma's variable geography. The eastern side of Oklahoma is lower and contains extensive forested areas. Central Oklahoma contains a transition from forest to prairies, and in the northwest there are flat grasslands. With changes in geography, you would expect changes in climate and weather. We will be sure to explore this expectation shortly. Here, the daily solar energy availability at the Mesonet station with ID Acme is plotted. The data are cyclical, generally peaking in the summer months and troughing in the winter months. This trend is certainly to be expected, as Oklahoma is well north of the equator. In summer months, the sun rises earlier, sets later, and rises higher in the sky. It may also be that there are a greater proportion of sunny days during summer months. Year to year, the data does not appear to vary significantly. Winter months may have greater variability than summer months, day to day. Now, instead of daily energy for a single station, let's look at the yearly and monthly energy for all stations combined. There is little variation year to year for all stations combined. The cyclical trend is again seen in the monthly data. We can look at the distribution of energy values as well, year by year. As with the totals, year to year, the distributions are very similar. 1994 has a single outlier that changes the shape of its distribution. Interestingly, there are 3 main groups of points in each distribution. High values, just below 30 million, medium values, just above 10 million, and low values, just above 0. Analyzing the energy distribution by month, we again see the cyclical trend, peaking in summer and troughing in winter. The shape of the distributions varies by month. In summer, there are many high values with a long tail down to 0. In winter months, there are 2 distinct groups of points, those at the top of the distribution for that month and those near to 0. These distributions are combined to form the yearly distribution shapes. This plot is a map of the total energy by station location. Total energy is highest in the west and lowest in the east, likely a result of the varying geography and climate. Let's take a closer look at a couple of the weather forecast variables. The average forecast total cloud cover is plotted as contours over a map of Oklahoma. Cloud cover is highest in the east and lowest in the west, inversely correlated with total energy, unsurprisingly, as clouds obscure sunlight. The total forecast downward shortwave radiative flux at the surface has the opposite trend as cloud coverage. Radiative flux is a measure of power per unit area. Let's move on to statistical data analysis. This analysis is separate from the machine learning task, but here we are looking to apply some statistical inference techniques that may create value for a utility company. Bootstrap inference is useful for determining confidence intervals on mean and standard deviations calculated from samples of a population. Here, we will determine confidence intervals for the mean daily energy availability for a single station for a given month. The value here would be that a utility company can quantify how likely it is that the mean energy for a given month will fall in a certain range. This quantification may help with long-term and contingency planning. The distribution of the daily energy values for share station for all days in July from 1994 to 2007 is shown here. The distribution is certainly non-normal. Let's take 10,000 sets of samples with replacement from this distribution and calculate the mean of each of those samples. We can plot a histogram of the replicate means and calculate the values between which 95% of the means fall into. These are the 95% confidence intervals. We can also calculate the mean of the replicate means. We can apply the same technique to share station in January, the distribution of January values being shown here. The replicate mean histograms are plotted for January in orange and July in blue. We can see that there is essentially zero chance of the mean daily value for any given January being anywhere close to the mean daily value for any given July. If we were to repeat this technique for, say, every month or even every 2-week period, a utility company could quantify the expected daily energy values at a more granular level. This task has better implications for long-term planning as opposed to short-term, which requires more granular and specific predictions. There's another way to infer probabilities when you've got a distribution. That is, Bayesian inference. Let's again look at the January energy distribution. The way I've been taught to start a Bayesian inference problem is to think about how the data could have been created. You can reasonably say that the distribution shown here could be created by sampling from 3 different normal distributions, each with a different mean and standard deviation. Of course, each point would have to be assigned to one of these 3 distributions as well. We can use PyMC3 to build the prior and posterior distributions. The histogram of the actual data is plotted along with the 3 clusters drawn using posterior mean parameters. Clusters 0 and 2 converged quite well in the model, while cluster 1, the red cluster, did not converge quite as well. This result is unsurprising, as cluster 1 is sandwiched between the 2 other clusters, and many of the points in cluster 1 could just as easily be drawn from one of the other clusters. However, the clusters do appear to represent the data quite well. The model also infers the proportion of data points that are assigned to each cluster. We can create a simulated dataset drawn from the posterior mean clusters. The simulated data appears to be similar to the observed data. The posterior distributions could be used by a utility company to simulate the likelihood of a certain daily energy value in January. Of course, the same technique could be applied to each month of the year. Now, on to the main event, machine learning. As discussed earlier, the goal is to predict the daily solar energy availability at each of the 98 mesonet stations given daily weather forecasts. 3 types of models have been built, evaluated, and compared. ordinary least squares linear regression, stochastic gradient descent, and gradient boosting regressor. When deciding on a method of model evaluation, it is crucial to consider the type of data being used. In our case, the data is time series and displays autocorrelation from year to year. For cross-validation testing, instead of randomly generated folds are split manually, segmented at year beginnings and ends. This choice was made to ensure temporally distant samples existing in each fold. The data is split into 5 contiguous folds with the test set removed for final validation. This test data is not used at all in hyperparameter optimization or cross-validation. Each model is evaluated using an average cross-validation mean absolute error, test data mean absolute error, and test data adjusted R-squared. The first model we will use is linear regression. It involves fitting a hyperplane to a set of points in n dimensions, where n is the number of features. Linear regression typically requires the following assumptions. 1. A linear relationship between the target variable and features exists. 2. The data should not exhibit multi-collinearity. 3. Homoscedasticity, that is, constant variance, of residuals. 4. Normally distributed residuals. The first model is ordinary least squares with no feature selection. The 15 weather forecast variables at 5 timestamps for each day make up 75 features. Latitude, longitude, elevation, and month of the year have also been implemented as another 4 features for a total of 79 features. Let's test our assumptions of a linear regression model. Regression coefficients are non-zero, and the t-test p-values are very close to 0, indicating that the features do have predictive power, and it's very likely not by chance. Multi-collinearity can be tested using a correlation matrix of all features. The features looked at in this matrix are at forecast hour 0 only. We can see that multiple features are strongly correlated with one another. Let's remove the correlated features, keeping those with the strongest correlation with energy for the next model, and see how the results compare. Homoscedasticity, or constant variance of residuals, can be checked visually and statistically. On the plot of fitted values versus actual values, a set of perfect predictions would yield points along the red line. Points to the right of the line are over predictions and points to the left are under predictions. At low energy values, fitted values are consistently higher than actual. At higher energy values, fitted values are consistently lower than actual. The Bruce-Pagan test confirms through the rejection of the null hypothesis that the residuals do not have constant variance. Lastly, the linear regression model predicts negative values, when in reality it is not possible to have negative solar energy availability. The test data show the same trend with the same conclusion. The final assumption is normally distributed residuals. We can check this assumption visually with a histogram or quantile-quantile plot and statistically with the Anderson-Darling test. The histogram appears to have more weight on the negative side of the residuals. The quantile-quantile plot would ideally show the points along the red line, which at the tails they are not. The Anderson-Darling test null hypothesis is rejected as the test statistic p-value is very close to 0. We can say with a high degree of certainty that the residuals are not normally distributed. Let's build 2 additional models with reduced features to fix one of our assumptions of no multi-collinearity. Model 1b used a smaller set of features than Model 1a, removing features that were correlated at forecast hour 0. Still though, there are many strongly correlated features when all forecast hours are considered. Model 1c uses a much smaller set of features, none of which have an absolute R-squared value of greater than 0.7 between them. Comparing the results of the 3 linear regression models using the evaluation criteria, we see that reducing and then eliminating multi-collinearity did not improve the models, rather the contrary. Model 1a has the lowest CVMAE test MAE and highest test data adjusted R-squared. This result implies that multicollinearity was not a problem for this dataset in terms of implementing linear regression. The models do have predictive power. The test MAE for Model 1A is 13.3% of the mean energy value. The predictions correlate well with the actual values, as shown by the adjusted R-squared values. The next model type we will use is stochastic gradient descent. SGD is a process for optimizing a linear regression by minimizing a cost function by following a gradient. Stochastic means that the process is linked with random probability. Samples of the dataset are randomly selected for each iteration. This is a very efficient process. As it is sensitive to feature scaling, the features are scaled prior to fitting. There are several hyperparameters to be tuned. Hyperparameter tuning for this model is done using grid search CV. A subset of the overall hyperparameters were tuned as a result of time constraints for this project: alpha, max iterations, epsilon, and the loss function type. The model results in very similar evaluation criteria values as Model 1A, the simple linear regression. Perhaps with further hyperparameter tuning, the model could be improved. As with the ordinary least squares models, the residuals violate homoscedasticity and normality. The final model type is a gradient boosting regressor. GBR is an ensemble prediction process. That is to say that it uses a collection of predictors to give a final prediction. The purpose of ensemble predictions are to reduce noise, variance, and bias. The process uses boosting, meaning the ensemble of predictors are made sequentially, and observations with higher errors are more likely to appear in subsequent predictors. Each predictor is a regression tree. As with SGD, there are several hyperparameters to be tuned. Like for the SGD model, a subset of the hyperparameters have been tuned using grid search CV, number of estimators, max features, and max depth. Running grid search CV for this process took about 6 hours for 81 fits, and it was run using an Amazon Web Services EC2 instance to avoid stressing my laptop CPU for long periods of time. The model resulted in the best evaluation criteria of all models, the comparison being shown on the next slide. As with the ordinary least squares models and the SGD model, the residuals violate homoscedasticity and normality. As we just saw, the gradient boosting regression model performed the best for all three evaluation criteria. The GBR model test MAE is 11.9% of the mean energy value. Because we are using MAE, the errors are analogously weighted, meaning an error of 2 is twice as worse as an error of 1. We can calculate the percent differences between test MAEs. There is a greater than 10% decrease in test MAE from the OLS model to the GBR model. Comparing the fitted versus actual energy values for the two best performing models, we see that the GBR model has a much cleaner and organized distribution of points. The GBR residuals do not have constant variance, but they are much more evenly spread around the perfect prediction line when compared with the OLS model. The same trend is seen in the test data. The final comparison we will make is a comparison of histograms of fitted and actual values. It is clear that the GBR model produces a set of predictions much more similar in frequency to the original data compared to the OLS model. In conclusion, the linear regression models have predictive power, but plenty of shortcomings. Most notably so is that low values are consistently overestimated and high values are consistently underestimated. The gradient boosting regression model performed the best when evaluated using cross-validation and test mean absolute error and R-squared. To put the results into further context, test MAE for these models were comparable to those on the Kaggle contest leaderboard, although the leaderboard is calculated using different unreleased test data. There is plenty of further investigation that could be done for this project. Additional time spent tuning SGD and GBR hyperparameters may yield better results. Learning rate is often an especially important parameter to tune. It would be interesting as well to train 11 different models using the 11 different weather forecast models provided by the Global Ensemble Forecast System, and then use an average of those predictions. Lastly, some sort of distance-weighted average of weather forecast values taken from multiple nearby forecast grid point locations could be used as the weather forecast variable features. I had an excellent time working on this project. I definitely learned lots, and I'm certainly looking forward to my next project. Thanks so much for watching. I hope you enjoyed. And please feel free to reach out with any feedback or questions you may have.